Hello and welcome to the segment 3 in this week. So in this segment, we'll study how we can train the neural network that we have just built. So the training is nothing but a sequence of operations, and we are doing that operation or those set of operations again and again. So there is a loop involved. So what are the steps? So if you see the training process, so we calculate the forward pass. So we have initialized this enter weight parameter or enter weight vector or the matrix or whatever you call it per layer, or these all the layer in combination. This multidimensional weight parameter you have initialized with some random value. You do the forward pass with some input, right? You get some loss value, and that loss value is nowhere close to the minimum, right? So we have to go to the minimum loss. What we do? We do the backward pass. What we do? We calculate the gradients of this loss function or loss value with respect to each parameter that is used in the forward pass. So this gradient calculation is basically the next stage after the computation of loss. So that means I need to have the input ready, I can do the forward pass, I can calculate the loss, then I can calculate the gradients, right? Gradient of the loss function with respect to all the different weights, and then we can see whether I will move towards to minimize this loss. So basically I'll update my parameters. So that is basically the next step after you do the backward pass or gradient calculation. So after we compute the gradient and we see that how much change I need to make in my weight vectors, we do the updates in the weights, then we do another pass, right, and see these updated weights has reduced the loss how much, that we can see. And similarly we will do this process again and again. So how many steps are involved? We have the forward pass, we have the loss computation, we have the backward pass after that, and then we have the step, which is what? Step means we will update the values or update the weight parameters and biases by the gradients that we have calculated, and then we will set or we will reset the gradient values for the next pass, right? And we repeat this loop again and again till we achieve the convergence. Convergence means what? Till we achieve minimum loss, which is towards 0 if we can think of. So now we will study how to write this training loop, how we can use different optimizers in this backward pass or gradient computation, how we can use different loss functions to define this loss, and what are the different rate schedulers are there which will accelerate or decelerate the training process. And also performance in terms of the quality of the training is also connected to each of these choices that you will make in this training process or training loop. So we will see also how to use the validation loop to test or evaluate the model that we have just built, and checkpointing, and use the checkpoint or saved model in our full training pipeline. So in this slide you are seeing training loop step by step. So there are 6 lines here you can see which are important, and this defines the clear set of training method. Okay, so here you can see that for each epoch, so this is basically the epoch loop which will go through the, after we run through all the data, then we complete one epoch for the training, and we are calling this train. Basically this will do the training, and this is my train loader which is loading the data, and then we have the stage where we are doing the optimizer resetting, then forward pass, and then computing the loss function, and then computing the gradients, and then computing the or updating the weights. So you can see that we are clearing the gradients in the beginning, because in the beginning itself you can have something in the gradient that we are using, right. So that should not impact the gradient calculation, and in the subsequent iteration I anyway need to reset the gradient values. So 0 grad will reset the gradient values, which will be used to update your parameter, okay, in this stage. So again, here we are clearly defining the stages as 6 steps. One is the training mode, then we have the gradient computation, clearing the old gradient, then the forward pass, compute loss and compute gradients, and then updating the weights. Now each step matters because 0 grad is used before the backward pass, because without clearing we will not be able to update the gradients. Model.train at start of each epoch will actually see, or it will differentiate between the dropout and batch normalization, because if we use evaluation we will not use dropout and batch normalization, but training means what? Here we are defining this training in the beginning itself, so that if there are dropout or batch normalization layers are there, it should not mislead the result. So forgetting this will give misleading result. So that's why this is used in the start of the epoch. Loss.backward will be used before the step, because before updating we should compute the gradients, and the optimizer needs the gradients that backward that is computed in the backward pass. How it is computed? By using autograd machine, okay. And then obviously we need to move data to the device before the forward pass. So that's why moving of the data has been done or performed before the forward pass itself. So if we do not get the data before that, we will get runtime error. Next, we are seeing the complete training step annotated. Now here we are seeing the training steps. So in this you can see that we are using 0 grad, set to none equal to true, which is the optimizer that we are defining here. There are several optimizers that I will come, and with context is used here. This is optional, because if we want to use, let's say, mixed precision in my training, I can use with torch.cuda.amp automated mixed precision that is coming from CUDA, right. This also we have talked about before, and then autocast, it will do the autocast in the changing the different data types from another type of data. So logits are basically the final output neurons. This is equal to the model X, and loss. So this is the forward pass, and this is the loss definition, loss function. Here cross entropy loss is used, applied on the logits, and Y is the output. So this is basically your loss. Now here interesting thing is that this part, the forward pass and the loss function computation, is basically inside the autocast or the mixed precision. Basically here we are doing the training in mixed precision. If we do not want to do, then this context is not required. With context here is not required. Then we can do the backward pass, backward through the loss, scaled loss, and then the gradient clipping is usually done for modern LLM training pipeline, because gradient clipping will, because there are many such stages will be happening to resolve or eradicate the vanishing gradient problem. We usually do the gradient clipping, and then the optimizer steps will actually update the parameters, and then the loss scale will be updated. So this is basically the typical LLM training pipeline. Okay, so the before we have seen usually the neural networks, convolutional neural networks, those are defined as previous. Here for performance we are defining the pipeline for LLM training. Optimizers are the key ingredient for defining or computing the gradient, because optimizers will update the weights with the gradients, right. So update rule will be based on what type of optimizer that we are using. Here weight is updated weight, and this weight is the old weight. We are negating the computed gradient plus momentum into the previous update, learning rate is there. So this is basically the stochastic gradient descent rule that you usually see. So here these are essentially your hyperparameters for your model. Now hyperparameters are what? The parameters that we define or give as user, which can be changed and which will impact also the model performance or basically the training performance. I will not go details into the each gradient descent or stochastic gradient descent algorithm or any other optimizer that we are going to see, but we are talking about more about the hyperparameters that are used here. Here the hyperparameters used momentum, weight decay, usually stochastic gradient descent or SGD optimizer is used like torch.optim. This optim has many such optimizer algorithms that are already implemented, so we can use them. So SGD or stochastic gradient descent are good in convolutional neural networks for vision tasks. So in the computer vision algorithms like image classification, image segmentation or object detection, so this type of tasks we usually use stochastic gradient descent. Obviously this can depend on what type of algorithms that we are using, like ResNet architecture trained on ImageNet uses SGD. Okay. Learning rate defines how faster the training will happen, because if I increase the learning rate, you can see that the reduction in the weight will happen faster, right? So if I use higher learning rate, that means I am trying to go or I am trying to learn faster. But that does not mean that it will always converge fast. So that's why there are different ways to use the value of learning rate. So there are this hyperparameter tuning kind of step are there, where we can tune these hyperparameter values based on what type of tasks that we are training this neural network for. Here is another optimizer, that is ADAM optimizer. ADAM optimizer is widely used in NLP tasks or natural language processing tasks and generative models. And here the parameters are LR, which is learning rate, beta, epsilon and weight decay, and you can see the usual values. You can find these usual or the traditional values to start with in many such already pre-trained models, and you can use those values to start with, and you can see how these model parameters impact the training loop. Okay. There is also ADAM weight decay, another optimizer, ADAM W. This is widely used for your modern LLMs or transformer models like vision transformers or VIT, BERT model, which is NLP model and basically or natural language tasks. So diffusion models are also using this type of optimizer mostly, and you can see the parameters, hyperparameters, learning rate, the weight decay, the fused, whether this will be fused true or false. Fused operation will actually fast or accelerate your training in the CUDA. So obviously you can use different optimizer for your model definition for different purposes. Now this learning rate that we talked about, learning rate will define how fast this training can happen, right? So you can see that we are using learning rate here. Each optimizer will have these learning rate values, because this is the primary hyperparameter which will define the speed at which you are learning. So there are different ways to control the values of learning rate. If you fix that in the initial stages of the learning or the training phase, that means you are using static learning rate. Static learning rate, you can use very low learning rate which will slow the entire process of training. You can use higher learning rate which will try to faster the learning process, or you can use adaptive learning value or learning rate values. Usually in the modern LLMs or any neural networks that we train, we usually use adaptive learning rate value. That means it will not be static throughout the training process, and that is very important, because I do not want to go slow or go fast in every stage of my training process. So if you can segregate training process into 3 phases: starting of learning, middle of learning or training. So here we are actually training the AI algorithms, means we are learning the weight parameters or the parameter values which will reduce the loss. So that is the main goal here. Now, if I segregate these training phase into 3 phases: initial phase, middle phase and the end phase. So that means in the initial phase I try to go slow or I try to go fast. In the middle phase I try to go slow or I try to go fast, or in the last stage or the end stage I try to go slow or the fast for the training or the learning. So usually we follow different strategies like cosine annealing. It will smoothly decay the learning rate throughout the process. As you can see, scheduler equal to torch dot optim dot Euler scheduler dot cosine annealing. So basically this is the algorithm that are used, applied on this optimizer. Whatever optimizer that you have defined, that will get this Euler value not as a static value, rather it will be adaptive throughout the training process by this scheduler. Okay. So that's why we usually use learning rate schedulers. So here we are using cosine annealing, which will slowly decay or slowly reduce the learning process or learning rate throughout this process. One cycle Euler which will warm up, then the cosine delay will happen. So that means first we are trying to go faster in the initial phases because nothing much to learn. So we will try to learn the let us say coarse grained features in the beginning. So that means we can do the initial phase bit hurriedly. So we will try to increase the values and then we will do the reduction decay after the initial phase. So that is another way of doing the scheduling of learning rate. Okay. We usually use linear warm up. So we will linearly warm up, then we will fix the cosine decay. So that means it will steadily decay the process. So middle phase it will kind of learn slowly, the learning rate will decay throughout the end. So in the end we try to learn many minute details of the features. So that's where we try to reduce the learning rate towards the end of the process. So here is one such scheduler that we have just seen, and it is standard for transformer training, and you can use that for your any model training. So in your convolutional neural networks, diffusion models and so on and so forth. As I have mentioned, loss functions are widely used in the end. So for classifications we usually use cross entropy loss. So cross entropy loss will take the logits, right, raw logits, and apply log softmax internally, and it will do the smoothing if we do smoothing. So basically this is one way to define the loss function. Here criterion is the cross entropy loss, logits we can define, and then we can define the scores of the loss, which will be taking this logits value. Logits is basically the output of the last layer before applying the loss function or the loss activation. Here we are applying the softmax. So before applying the softmax, whatever the neuron values are there, so those are called logits, which is the output of the forward pass, and taking that and the labels we are creating this or calculating the loss scores for each level here. So this is widely used for your classification. Similarly, you can have this binary classification, right, BC with logit loss. For binary classification you can use this criterion. Similarly, regressions usually use the mean squared error loss or L1 loss, smoothened L1 loss. So one such smoothened L1 loss is Hoover loss. By the way, these functions you can go inside those functions and see how the algorithm is defined or implemented. It does not necessarily mean that you have to use these loss functions by rule, but basically it will ease your process. You can implement your own loss function and you can use it. also. For sequence modeling, we usually use cross entropy with ignoring the index. So this is one such use of cross entropy loss where we do not want to index the entropies. So basically ignore index, we can make it false or 0. Similarly, custom loss functions like focal loss is defined here. Similarly, I told you that you can define your custom loss. Here is one such custom loss is defined and you can use it. So loss function selection is key for any algorithm or neural network that you define, and here is one such kind of prescribed list or widely used practices. As I said, regression uses MSE loss, language modeling use cross entropy loss plus ignoring the index, which are used in any sequence modeling, right. After the training, we need to validate the process of the training loop, right. So here we are defining the evaluation function where def evaluate, this is the evaluate function which is taking the model, the loader, and the criterion which is the loss function that we have defined, and device obviously where exactly we want to evaluate. Model.eval will do the so this is will disable, as I said, model.train will enable the dropout and batch normalization in the training mode, but if we want to evaluate, then we do not need to activate them. So model.eval will automatically switch off the dropout and batch normalization layers. So they will not impact your dimensions because it will have the same dimension. So model dimension will not get impacted. So basically we can switch off in the evaluation mode. Training loss, correct, total. So they these are evaluated or started with 0 values, and then the loader will load the values or the data, and then the logit will be calculated, and essentially the total loss will be calculated. So this is your, let's say, typical evaluation loop, okay, which is similar to your training loop, but here we are basically applying it for our evaluation, and model.eval will ensure that we are doing the evaluation of the model. We can do the checkpointing for saving full training state. Checkpoint equal to, you can define the entire structure here for defining the key and values pair. So what is the epoch value, what is the model object, what is the optimizer that we are using, and all these will be saved by using torch.save with this checkpointing feature in this path. It will save your model at this stage with all the values of validation loss, validation accuracy, the scalar which is the loss value, and then the scheduler, what is the scheduler, the state of the learning rate, and so on and so forth. We can resume from checkpointing. So we can load the state of the checkpointing which we have saved already, and that can be used from this path and loaded into this model state, and then we can start the model basically running, okay. So and obviously we can separate the checkpointing whether the validation loss improves or not, and based on that we can actually checkpoint, or we can save, or we can retrieve the checkpointed or saved model, okay. So 6 main steps: model.train, zero grad, forward pass, loss function computation, backward, and step, which is basically updating, right. Missing or reordering any step will basically give you wrong result in the training loop, okay. AdamW is widely used for your LLM training, and you can use any other optimizer. You can see the list of optimizers also in the Python handout that we will share. Also the cross entropy loss or any other loss function that you use for your specific task you can define, and many other custom loss function also you can define. We can have validation loops separate from my training loop, so that the dropout, batch normalization, this type of normalization layers are switched up, okay. And in the end we can do the checkpointing based on what type of, at what stage we are trying to save the model, and basically then we can retrieve the model later also to train or resume the training from that particular state. Okay. So with this the training loop is finished, and then we will move towards the next session for the data loading and performance optimization. Thank you.